Hello once again. In this part, we are going to start with the intersection of two circles, how they intersect and how they behave, and what are the different cases that they form. So let's begin. Now we are going to start with the intersection of two circles. Now suppose that we have these two circles like this. Let's say they be C1 and C2, the two circles. Now the main point of looking at these two circles is you can see that there are various lines. All these solid lines are tangents. So the first of all the case is that how many tangents you draw and what is the difference between these two tangents. So if there are two circles which are not intersecting or which are at a distance apart, and you can see that they are neither intersecting nor they are touching. Actually, if the circles are neither touching nor intersecting, then there are four tangents can be drawn. Now, how to differentiate these tangents? So we have a general notations to differentiate that which tangent is what. So let's see what are these. Now these two tangents, this tangent and this tangent, you can see that these tangents are kind of direct tangents, so we call them as direct common tangents. First of all, both the tangents are common to both the circles and they are kind of a direct tangent. We have just given them a name by just the looks. So these are called the direct common tangents. These two tangents are then called as transverse common tangents. So direct common tangents and transverse common tangents. So this is a general notation about the tangents that and the naming. But again, the circles can be intersecting, non-intersecting, or they may touch each other. So how do we know that what is the behavior of circle with each other and how many tangents can be drawn? Let's see this. A case 1, when both the circles are non-intersecting and one lies outside another. This is an important thing. They are non-intersecting, but it can be the case that one circle lies completely inside another. So here also they may not touch, they may not intersect, but that is why we have specified the condition that both the circles are, one circle is, they are not inside each other. They are lying outside and they are non-intersecting. So here, as I have already told you, that these two tangents are direct common tangents and these two tangents are transverse common tangent. Now the condition for both the circles to be non-intersecting and lying outside is the distance between their centers has to be greater than R1, R2. Now what is R1, R2? That means R1 plus R2, and the distance between the center is, you can see that O1, O2, I can say the distance between center. You can say this, you can clearly see that this is R1, this is R2, but this whole distance from here to here, which is O1, O2, this is O1, O2. So if the two circles are completely apart, then the sum of their radius is smaller than the distance between their centers. This is also one of the obvious things. So if you know the equation of both the circles, then by checking this condition, you can tell me that whether the circles follows this condition or not. Now here in the previous thing, we know that there are two direct common tangents, two transverse common tangents. We only know the equation of tangent. We don't know as of now how to differentiate between which is a direct common tangent and which is a transverse common tangent. So here is the first working rule to find out the direct common tangents. Direct common tangents, these are the direct common tangents. So let me name it again for you guys. This is direct common tangent. We are finding out this as of now. So this point plays very important role. This point Q plays very important role. What this Q point is doing is that, look at this point O1, O2 and Q. Q divides this O1 and O2 externally in ratio R1, R2. Q is dividing this join of O1, A2 externally in ratio R1 and R2. So if you know O1, if you know O2 and you know the radiuses, you can find this point Q by section formula. We can find this point Q, okay. We know the ratios as well. So we know this point. Now this point is intersection of both the direct common tangents. So we have one point. We have one point which lies on both the tangents. Now we only want to know the slope. How can we find the slope? So to find out the slope, we have our very basic definition, which is the condition of tangency. That is the perpendicular, or you can say that the perpendicular distance from both the centers to the tangents has to be r1 and r2. Okay, so we can substitute these values of r1 and r2 and we can get. Remember that what is the point that is differentiating? Obviously these transverse common tangents are also going to satisfy these conditions. Okay, that the length of perpendicular from one to the center lies on its radius. So these transverse common tangents are also going to satisfy this condition. But what is the point that is differentiating from direct common tangents to transverse common tangents is that they are passing through Q, which is dividing the O1 O2 externally. So this is again a very simple case. Find out this Q and then apply the condition of tangency that the distance from center is r1 and r2. You need to remember that when you use the distance formula, there is a modulus. So with that modulus, there will come a plus minus sign. So there will be two values of m. If you look this equation, which is previously, so the coefficient of x is also going to be m. So when you write this equation, there has to be 1 upon m square term, which will give us a quadratic in m, or you can say two values of m. So this is the way to find out the direct common tangents. Similarly, you can find out the transverse common tangent as well. Instead of using the point Q, we are going to use the point P. Q point was dividing the O1, O2 externally. P points divides O1, O2 join internally in the same ratio R1 is to R. And after this, you can follow the same method that the distance from center to these radiuses are R1 and R2. So again, the difference is created by these points. If you found the point which is by external division, you will get direct common tangents. If you find the point by internal division, you will get transverse common tangent. So in this way, you can differentiate as well as you can clearly find out which is direct common tangent and which is a transverse common tangent. Now, this was the case 1 when both the circles were apart, they were separate. Now case 2, when both the circles touch each other externally. So when both the circles are touching each other externally, then again this point Q, it still follows the same condition. Now you can also see that this P point is also following the condition of internal division, and we can clearly see that the ratio is R1 and R2. So this one radius is the transverse common tangent. We have only one transverse common tangent here, transverse common tangent. These two are again direct common tangents. This is the point Q for external division, and this is the point P which is doing the internal division. What is the condition? I can clearly see the condition that the distance between O1 and O2 is equal to R1 plus R2. So again, it's a very obvious rule that distance between the center has to be equal to sum of the radiuses. Now the point of contact, again P, as I said, that we can find it by using the internal division method. Now case 3. Previous case was an external touch. This case is internal touch. The circles are still touching, but they are touching internally. In this case, you can see that we can draw only and only one common tangent at this point of contact P. We can draw only one common tangent. We know this value of P. So first of all, what is the condition for internal touch? That O1, O2, that is the distance between these, is equal to mod of R1 minus mod of R2. How? Look, R1 is actually distance from here to here. This is R1. R2 is this distance. This distance is R2. if you subtract from R1 to R2, we are left with this distance, that is O1, O2, distance between both the centers. So obvious condition, O1, O2 is equals to R1 minus R2. Again, the point of contact divides O1, O2. Here you can see that the point is outside. So again, it's obvious an external division, but the ratio remains same. So we are following one thumb rule, that is the ratio is same in the division. It's just that you need to look that whether you are searching for the internal division or for the external division, and the kinds of tangents will change based upon the fact that what is the interaction between the circles. Now case 4 is that when the circles intersect. When the circles intersect, we have a straightaway condition that the distance between these centers is actually less than R1 plus R2, but it is greater than mod of R1 minus R2. Okay, so that the circles do not lie inside completely. Here, there exists two common tangents only. What are those two common tangents? They are like this. One is this, one is this. Again, to find out these two direct common tangents, we have the case that we know, find out this point Q by external division, and then rest method same. Here there is one interesting thing. When the circles intersect, one can ask you what is the angle of intersection of two circles. So angle of intersection of two circles, if you look carefully, then suppose that at this point P, the two circles are intersecting. Obviously they are intersecting here as well, but let's take this point P. What I am going to do, at this point of intersection, I am going to draw tangents to both the circles. This tangent is to this circle, this tangent is to this circle at the point of intersection, that is P. Now the angle between angle of intersection between the circles is actually the angle between the tangents at this point of intersection. That means angle of intersection between the circle is nothing but angle between the tangents at that point of intersection. Now, so we need to find out this theta, or you can say this theta. Okay, this is the radius, this is the tangent, so they are perpendicular. This is the tangent to this circle, this is the radius, so they are again perpendicular. Now that means this is 90, this is 90, and this is theta. So this whole angle I can write it as 180 minus theta. Okay, and if you look at this P O1 O2, O1P is the radius, O2P is also the radius, O1 O2 is distance between the centers. I know the length of these three segments. So if you look into the triangle P O1 O2, I can apply the cos 180 minus theta formula by which I can find out cos theta. Okay, cos of 180 minus theta, and by which I can find out cos theta. Okay, here we have taken mod because we are actually interested in the acute angle. So cos of theta is again O1P square, that is this, then O2P square, that is this, minus O1 O2 square divided by 2 O1P and O2P. This is the simple cos theta formula in terms of sides. But we know that O1P and O2P are the radiuses. So we can write the radius in terms of G and C. And again we can write the O1 O2, which is the distance between the centers. We can also express in terms of G and F and C. So this is the one formula in terms of radius and distance. This is the formula in terms of if you have the equations and if you want to find out the angle of intersection between the circles. You can directly put the values of G1, G2 and F1, F2 and C1, C2 from the equations, and you can directly find the angle of intersection between the two circles. This is an important formula. You have to remember this. This is a direct result. Now, I can also say that again, the same thing, that O1P square is R1 square, O2P square is R2 square minus distance between the center divided by 2R1 R2. That means that whatever angle the circles are intersecting, you can find it out by this method. But we have a special condition which says that orthogonal intersection. What is an orthogonal intersection? Orthogonal, that means they are perpendicular. So intersection of circles when they are perpendicular. Circles intersecting at 90 degree, that means their tangents are intersecting at 90 degree, or the tangents at the point of intersection are perpendicular to each other. That means the angle between the tangents is going to be 90 degree. This is our cos theta. If theta is 90, that means cos 90 is 0. Or I can say 2g1g2 plus 2f1f2 is equals to c1 plus c2. This is again a very important result. You have to remember it. This is a direct result for orthogonality between the two circles. So this is again a result that you need to remember. 2g1g2 plus 2f1f2 is equals to c1 plus c2. Now we'll move to the last case, when the circles are lying completely inside another circle. That means that this distance between O1 and O2, that is the center, is even less than the difference between their radiuses. You can see that I cannot draw any common tangent because there is no common point, and the circles are also lying within this other circle. So I cannot draw any common tangent. Now let's move to a checkpoint. Suppose that we have a circle like this. Its equation is given by this, the smaller circle. We need to find out the radius of this bigger circle. It is given that its center is of form h comma h. If the center is of h comma h, the first thing that strikes in my mind is that this distance is h, and again this distance is h. You can see that the circle is touching the axes, so this is also 90 degree, this is also 90 degree. This is the information that I can get only from the figure, just by looking the figure carefully. Now we need to find out this, let's say this point be K. We need to find out the length of CK. Now because this, if you look at the triangle COD, this side is H, this side is H, and it's a right angle triangle. That means this angle is 45 and this angle is also 45 because it's an isosceles right angle triangle. So this is 90 and the rest of the two sides are 45. Now at the first look we all think that okay, we know these two sides, so let's apply this 45 degree or cos formula or sine formula, let's find the hypotenuse. But it's of no use to us, because if you look carefully then you don't know what is this small distance. So what we are going to do is that we are going to play smart. We need to find, what I'm saying is that I can say that CB, that is this length, okay, CB is nothing but our radius, the desired radius R plus 2. This is B point, which is the center of the smaller circle. So CB is this, from here to here it is R, and then plus the radius of smaller circle. CB is R plus 2. Similarly, what is BE? BE is nothing but H minus 2. Why? Because from here to here this is CB. The whole distance is H, and from this B point to this point the distance is the radius of smaller circle, which is 2. Okay, how it is 2? We can calculate it easily from this point. Okay, so this is 2. Now if I look at this triangle, because this line is parallel to this line and this angle still remains 45, this angle is also 45. So I can apply cos 45 very easily. That means cos of 45 degree is equals to base, that means this side. Base is H minus 2 divided by hypotenuse, that is R plus 2. We know that cos theta is nothing but 1 upon root 2. So 1 upon root 2 is H minus 2 divided by R plus 2. We are interested in finding out that what is this R? What is this R? But R is equal to H because this CD length is also the radius. So I can write it as R minus 2 divided by R plus 2. If I simplify, then I'll get R plus 2 is equals to root 2 times of R minus 2. That means I get the value of R as 2 times root 2 plus 1 divided by root 2 minus 1. This is your radius. So again, the question was easy. It's just that can you sense all those information that are there in the figure as well as question. Let's move to one more question. We need to find out the locus of center of a circle that passes through A comma B and cuts this circle orthogonally. That means we need to find out the locus of center of circle. Remember that you need to find out locus of center of circle. So let's say that the circle is, let's suppose that the equation of this circle is the general equation x square plus y square plus 2gx plus 2fy plus c is equals to 0. It passes through this a comma b. So let's say a square plus b square plus 2ga plus 2fb plus c is equals to 0. Let's say this is the first deduction that we have. Now this circle and this circle intersects orthogonally. That means 2g1 g2 plus 2f1 f2 is equals to c1 plus c2. So twice of 0 into g plus twice of 0 into f is equals to c1, that is c, c2. c2 is nothing but minus a square, because this a square will come here, minus a square. That means c is equals to a square. We got the value of this c. If you put the value of this c here, and we need to find out the locus of this minus g comma minus f. So I can say that let's put minus g as x and minus f as y. That means minus 2xa minus 2yb, c is a square, so this a square and this a square will become 2a square plus b square is equals to 0. That means my locus becomes 2xa plus 2yb is equals to 2a square plus b square. Again, it's the simple thing. Whatever the question is saying, do it step by step. You'll automatically reach to the answer. Meanwhile, if you have any doubts, you can log on to askIITians.com and you can go to the discussion board. On this discussion board, you will form a form on the right hand side. Select the category in which category your question falls, post your question and get an answer. Here, the experts of Ask IITians will answer all your queries within 24 to 48 hours for free. So this is it about the intersection with two circles. I hope that you have carefully noted down all the 5 cases and you have understood that what is the difference when they are non-intersecting, intersecting, touching or inside. Also, please carefully note the orthogonal intersection condition. So this is it about this part. I hope that you have understood. In the next part, we'll start with the equation of director circle and chord of contact. Thank you for watching.